Hello, everybody. Today we're going to continue advanced procedures. In the last class, we learned basic concepts about stack, and we know how the stack is important. And I hope now you know at least the basic idea of how the push and the pop works. So these are very two important concepts. And I hope that you know that how the ESP, which is very important for your knowledge as a programmer and in your test, quiz, or midterms, it is very important to understand how push and pop affect the instruction pointer, right? The stack pointer. Okay, and we also know that we have the instruction pointer that is going to be affected as well. And we know that the instruction pointer, it comes to be very important when we learn the call and return. So these are the things that they're going to play with the instruction pointer, right? So as you know, if we say call, you know call is nothing but what? Push, right? You agree? All right, and return is nothing but what? But pop, right? Because when we call a function, we know that we're going to do two things, right? If you remember. Okay, first we're gonna push, right, the address of the next instruction in the stack. And then the second thing we're gonna do is we're gonna update the instruction pointer. All right, so these are the two things that the call does. And the return also do something very interesting, and which is nothing but what? It is gonna do what? It is gonna pop the top of the stack, okay? And when it pops the top of the stack, it copies the return address, okay? So if it does that, it automatically gonna update what? The instruction pointer, all right? So these are the basic ideas that we learned in the last class. I will review them in the upcoming slides, and then we're gonna move into frames. So today we're gonna focus mainly on what is a frame and how a frame is created and how a frame is related to a method or a function call, okay? So this is what I was talking about right now. So we're gonna focus mainly on frames. Okay, so we're gonna see how those frames are used to handle parameters, to pass arguments, and to access parameters. These all possible based on a frame. So we're gonna understand what the frame is because we know what the stack is, right? So we know that we have a stack, but if this is the stack pointer that points at the top of the stack, right? So what if we have multiple functions? Shouldn't each function has its own space? Exactly, that is what we call a frame. So maybe this is for function one or method one. Maybe this is for function two or method two. So we can call this frame one, we can call this frame two, and so on and so forth. Why is that? Because when you create a frame, you have a better understanding of how you refer a local variable that you need to access from F2 to F1. Or you have an understanding of how to pass arguments from F1 to F2 because you need to know where that memory is. And that memory means the frame. Okay, so you're going to talk about these concepts today, and we're going to also learn how to clean up the frames or the stack, and then how you're going to save and restore registers. And we're going to play also, if the time allows, how to handle local variables. So we're going to have a very long day today, okay? And in the following week, we're going to talk about reference parameters and recursion. But recursion, you're going to look at the recursion in the class as well. This topic usually I don't cover if I don't have time. So I just leave it up to the students to read. And I don't really have time. I want to move to the floating point because you don't have much time, maybe 3 classes. So I will leave that up to you to read by yourself. All right, but we're going to cover the core thing, which is the second piece of the stack, which is the frame. Okay, so let's carry on. That's what I was talking about last time. So now we know what a push is and how a pop works and how the stack grows. It's going to grow from high to low, and we looked at that in the Visual Studio as well. And now we know what is the stack pointer, and we know when you see this directive, which is dot stack, this is the space you create. So this is your space. So that is the space right here. Okay, so you create the space, and then inside the space, you're gonna use the stack pointer to just follow or you're just going to trace where you add in that space. Okay, so this is something we already covered. We also learned how call and how return works, right? And we know, I just explained it right now. When you call a method or you call a function, you know that is the address of the next instruction. This is our next instruction. So the address is going to be pushed into the stack by the call instruction. This is all done by the call instruction. That's why they call it an instruction, because it does specific things, right? So it's going to do this, and then it's going to update the instruction pointer. By what? It's just going to go to the caller because it knows the name. That is the label. With the help of the operating system, is going to give it the entry point. So this is what we call the entry points. So it's going to get the entry points, and then is going to assign this to the instruction pointer. So the instruction pointer usually always points at the next instruction. Now it's going to go and point right here. Okay, that's what we did in the last class. That's what we learned. Okay, when we hit return right here, we know what the return is going to do, right? So the return is going to believe. So it's blindly believe. We could really trick the return, but we are not going to do it right now. In the next class, I would show you that once you have played with the lab, and then I think you're going to be ready for me to show you how to do some tricks, knowing the fact that return doesn't really verify, just believe. Okay, so the return here believes that the stack pointer really points at the right location. So if it really does that, then what we're going to do, it's just going to pop this value and you're going to assign it here. That's what the return is going to do, because return is nothing but a pop. Pop means the source is going to be the stack, the destination is going to be the instruction pointer. You see it? So that way we're going to guarantee that the instruction pointer now is going to go back and is going to point at this instruction, and then the execution is going to continue from there. Okay, so that's what we covered in the last class. And we also looked at the nested calls, right? And how we have multiple calls in here. If you see it, this is one call, this is one call, this is one call, and then this is what we did like going forward, right? So when we went up to here, that when we went to the call right here, that was actually the state of the stack. Okay, when these all those call instructions were executed. Okay, so that is the state now, or the status of the stack. It has all of them right here. Once we hit the first return, that's going to be our first return. This is going to be second return. This is going to be our third return. It's backward now. We are going in this way now. Okay, here we just moved in this way. Okay, so when we go back, every time we want to go back, I want to go from sub 3 to sub 2, then we just going to say return, and we know what return does, just going to pop, right? So it's going to pop the top of the stack. It's going to take this value and assign it to whom? Remember? It's going to assign it, you guessed right, you're going to assign it to the instruction pointer. All right, so we're going to go back to this return now, and this return is going to say, who's my caller? Okay, so now when the pub assign this to the, this is not an F, this is an I. So it's going to assign this. When it assign this, it's going to what? It is going to increment or decrement the stack pointer. Yeah, pub is always incrementing because we're going to the direction of the memory, right? So we're going to go back to this part. So when we hit the return number 2 right here, that means it's going to pop now. All right, it's going to pop the top of the stack because the stack pointer is pointing here. And that's the return address that is going to take us where? That is going to take us to the sub 1. So sub 2 now is going to go to the sub 1. And when we're going to go to the sub 1 right here, that is the sub function, we're going to hit the return. So we know when we do this pop, we know that the pop also is going to increment the stack pointer automatically, right? So it's going to point the return to the main. All right, so when we do this, it's going to assign this, right? And then now it points at the main. This is already done by the sub 2. And sub 1 now is going to say return. We know return is going to get the top of the stack right now, okay? And then it's going to assign it to the instruction pointer. So the instruction pointer is going to return the control to the exit. Do you see it? And when it does this, when it copies this, now it's going to incremented by 4. We don't know what it was pointing at before this point. We don't know. but it's going to go and point right there. Okay, so this is exactly some facts that I assume you have in mind right now, and these are very important. If you know just those things that I talked about right now, you are really having a basic understanding of how a program works and how a program or a method calls another method or another program or subprogram. Okay, so if we know this fact or these facts, then we're gonna carry on and learn frame, because now we know how the stack works. We know push, we know pop, we know the stack pointer. We go down, when we push it's gonna decrementing, when we go up it's gonna incrementing, and we know the amount is always gonna be 4 bytes as long as we are dealing with 32-bit programming, right? So this is a fact, we should have it in mind. The second thing that we need to think about is the call and return, that they are both what? Nothing but push and pop. And we know call is going to push and update the stack pointer. And then we know that the pop, it is going to pop, the return is going to pop, and then it's going to update the stack pointer, the instruction pointer, I'm sorry. And both of them, since they push and pop, they automatically going to change the state of the stack pointer, okay? So I'm using stack pointer and instruction pointer exchangeably. These are very two registers that you need to keep in mind. We're going to learn another register which is very important for understanding the stack, and you will see that just in a minute, okay? All right, so let's look at what's a frame. Okay, sometimes they also call it an activation record, so they call it different things. Okay, so when we're talking about a frame, we're talking about x86, Intel x86 frame. All right, so if we're talking about a frame, this is what a frame is. So it's an activation record. So what do I mean by the activation record? We always gonna have how many active record? We always gonna have one, right, guys? Because if function 1 is executed right now, then that is the active function. If it calls function 2, then function 2 is the active function, okay? So the frame is gonna actually organize this idea of who is active right now. And if some space, which is a space for another function, is not active, then how are we going to access this space? All right, so first let's see what the frame is. That is the goal that we need to understand. So it's an area of the stack, right? So this is actually a frame. And this is also a frame. I will show you that in a minute. And the whole thing right here is a frame by itself. I'll explain that in just in a minute. Okay, so it is like a memory, like we have reserved to either pass parameters, return address, save registers, or create local variables. We're going to cover each one of those just in a second, but this is what I want you to know, that the frame is a stack space actually, but it's divided based on caller-callee relationship, but still it's the stack. Keep that in mind. Area of the stack. Okay, so that is what the frame is. This is what we call the caller stack frame, and this is what we call the callee stack frame. These are, remember when I talked about the white line in the highway? You see it sometimes yellow lines on the sides and a white line in the middle. Are these physical? Are they going to deny your car from moving from side to side? Definitely not. But why they are there? They just help you organize, right? As they help cars know where they at, and they help like who is sitting where, so that way we know how many cars they're gonna go by the whole road. It's just a logical thing that helps managing the traffic. So the frames is logical things, it's not a physical thing, because the physical thing is the stack. But the way we manage the stack, or we form the stack, is just logically, so that it's gonna help referring to local variable or returning from caller to callee, and it's going to make programmers' life way easier. But this is logical things, like the white line in the highway, just a logical thing. It helps you as a driver to know where to change lanes, and it helps the police to do some other activities, okay? So this is exactly what the frame is, okay? So the structure, as I said, of the stack frame, it's not generic. So you should not consider this is true for everything. This is only true for x86, Windows system. Maybe you're gonna go to x86, Linux system, you might see different frame. But again, the concept is the same, a frame is a frame. Just, it's a way of dividing the space of the stack. in a way that is going to make referring to between caller and callee way easier. Okay, the referencing between these two active records or two frames going to be way easier. Okay, so in order to understand a frame, we know in order to understand the stack, we need to understand that stack pointer. But if you add the concept stack to the stack, which is you divide the stack into frames, then you need another register, which is we call the base pointer. And we will understand what's the base pointer. You can see the base pointer right here. Okay, so this is what the base pointer is. It points at this part. We will see why we need a base pointer. Okay, so let me motivate you for that. So the stack pointer is always pointing at the top of the stack, right? So this is a fact that we know. And every time we push or we pop, the stack pointer is going to move all the time. So it grow and shrink at a different rate, right? Or at a different times. It depends on how a system calls another system. All right. So the base pointer right here, it points at the top of the stack when the function is first called. So it's kind of a fixed point. Okay, so when you call this function right here, so that tells you, oh, this is the time when you call the function. It's kind of giving you, as I say, it's a logical thing. So you know, like from here downward is all related to the callee. Anything up above this part is related to the what? Related to the caller. We know that this is going to be related to the callee or to the called. All right. So if after this, if you want the stack pointer to grow, you don't need to worry about it. So you see the stack pointer is right here right now. Do you see it? So I don't care. But now if I want to refer to anything in the caller or anything in the callee, I don't want to ask where the stack pointer is. So I have a fixed point now. This is my base pointer. So this is always fixed unless you change it when you have another maybe caller callee. But right now, if you have this active caller right now, because the callee now maybe going to become a caller, right? But now we have the callee is now active, and you can use the base pointer to go up. If you go up, that's the direction of the memory. So if you want to access this value here, this is just a value, then you're going to say the base pointer plus 4. If you want to access this, then the base pointer plus 8. It's very interesting. If you want to access something in the bottom, then you have to say minus, right? Because we are moving in the stack direction, and the stack direction is the opposite direction of the memory, right? So this is the main memory direction. This is the main memory direction, right? And then this one is going to be the stack direction, right? So if we move to the stack, we know we subtract. So you can access this value right here by saying base pointer minus 12, right? So why minus 12? Why you have to go there? So this is going to be your 4, 8, 12. So you're going to be at the beginning right here, and you're going to read whatever the data you have. Okay, if you want to access this, then you're going to access here, which is 16. So you're going to have 4, 8, 12, and 4, 8, 12, and 16. You see what I'm talking about? So this is very important. So we know that the reason we need a base pointer is because the stack really grows like ups and down, all right? So this is, remember when I talked about figuring out a direction when you drive in a city? Back when I was in Colorado, remember when I said, if I am in Colorado and I'm lost, I will look for the Rocky Mountain because that's the west. If I figure out where the west is, then I can figure out my way. When I moved to Atlanta, Georgia, I was just like lost because if I'm lost, I don't know. I don't have a reference because my car goes all directions. All right, it's like the stack pointer. My car is like the stack pointer. It moves all around the space. This is Atlanta. The stack is Atlanta. But if I said, hey, I'm lost, I want to go back or I want to refer to something, I said, what is my reference? I don't have a mountain. It's a big city, all like very like buildings around you, and it's really hard to use buildings as a reference. All right. So this is exactly the same. If you have a frame and you want to know where to go, you need to have your Rocky Mountain. So your Rocky Mountain is going to be the base pointer because it's fixed. You fix it and you say to the stack right here, grow. So the stack grows in any way, ups or down, or maybe the stack goes to another function if needed. Okay. So that's the whole idea. You know that with the frame, we need to have two registers, base pointer and stack pointer. Stack pointer is going to be there anyway. Okay, so these two registers are the heart, right, of the x86 function call mechanism. So you need both of them. Okay, so why not just the stack pointer? Why if I just want to access this, I said, okay, this is the stack pointer, right? And then I would say 4, 8, 12, 16, 20. You with me? So I will access this part. That is not wrong. But you don't really know what, if you want to do this for the second time, maybe you're not going to add 20. Maybe you're going to add something else. Right now it's 20, but in the next time we don't know because the stack grows and shrinks, right? It grows and shrinks at different time and different pace, okay? But right here, if you say +4 is going to be +4 forever, right? Because the base pointer is fixed. It's not going to grow, okay? It's going to be just fixed right here. We're going to move this to another space if we want, but that's going to be a completely different relationship, okay? So that's why the upcoming slide is going to explain this, why we need the base pointer, because you can see the fact right here, because the stack pointer really grows and shrinks during the function call. So we don't know where is it exactly. So the offset, which is the address of local variables on function, relative to the stack pointer's change. Okay, so change is going to be really crazy. You don't know. So x86 used to just function with the stack pointer, and it was very difficult. It was inefficient. So that's when they produced recently, I mean, several years ago, they start thinking about, years ago, they start thinking about adding another register, and that's when they come up with the base pointer. Okay. So that is basically to simplify things. That is what the Intel did. Okay, so the base pointer, why we need the base pointer? Now we know what's a frame, and we know that we have two frames here, caller and callee frame. And why we need a base pointer? Now we need to understand why is the base pointer, right? So the base pointer is going to provide you with the current functions. So this is going to be your current function, that is the active. And then once you know this, it's going to be a fixed offset, which is here. That's a fixed offset. And you can refer to things in this direction or in that direction. It depends on what you need to access. So that's why we need a base pointer, right? So we're going to have a fixed point, and accessing elements or arguments inside the two the two frames right here is going to be way easier. Okay, so so this is really very fundamental, and I hope that you understood the key idea of the frame. What's a frame, and why a base pointer, and why stack pointer and base pointers are needed. So now we're going to move into how to create. Okay, so that is the idea of the creation, how to create a frame, right? Or how a frame is created. So I think you guys can guess, right? Can you think about it for a while, how the frame is called, or sorry, is created? We understand the call function, right? So when we say call, we know the call is going to do two things. Do you know how important is that? You know, right? It's going to push, right? And then it's going to do what? It's going to update the instruction pointer, right? So if it pushes, this is push, then it's going to, maybe that's the return address. Maybe before the call here, you have push 5. So right here, when you say push 5, that is the parameter. And then you're going to call a function. Right here, let's say we're going to say call method 1. So we know it's going to push, so it's going to decrement by 4, and then it's going to push the address of the next instruction. Whatever comes after call is going to push it right there. So this frame is going to be created by what? By the call, right? Or maybe another push functions. Okay, so the call function is going to determine the end of the caller. That is something I guarantee you. But whatever you have before here, it doesn't matter. Do you have to push values to the stack before you call? No, it depends on the problem you're solving. Okay, so calling programs pushes, right? So that's what happens sometimes. Maybe you're gonna have argument, if any, you don't have to, and you're gonna have the return address, and the call then calls the procedure, right? That's what the call does. So call create is the core components of the caller frame, which is the return address. This one, it depends. We don't need to have it. You will see that when you play with the example in the lab, okay? And then the call procedure, now that's the calling. And then the call procedure now needs to push what? The base pointer. If you find the base pointer, And if you go to method 1, the first thing in the method 1, you will find the first instruction, push the base pointer into the stack. That's why you find it here. And then you can do whatever in here. Okay, so you need to have that. You don't have to, but you need if you really want to apply the frame principle. Okay, so if that is the case, then now why are we pushing the base pointer? Because the base pointer, before you move it here, this is very critical. The base pointer, let's just look at it here. The base pointer was pointing maybe somewhere, I don't know, in the memory. So before we make it go and point here, so before we go and we make it points here at this part, it has a value because base pointer is a register. Remember that, right? So this register maybe have 0013, right? This value is important. It points at something right here. It's important for something else, not for me. So I would say, hey, anyway, maybe later we need to return this value, push this value inside here. So here you're gonna have 0013. And then now you are ready to say what? That's when you're gonna say push. And now you are ready to say what? You are ready to say move to the base pointer, what? The stack pointer, the ESP. So that's when you see the ESP and the base pointer they're pointing here. So instead of the base pointer, instead of this base pointer is pointing here now, you already updated it, you moved the stack pointer to the base pointer, then now the base pointer is no longer pointing here, it's gonna go and point right there, okay? When we wanna return later and we wanna go back to this part and we're gonna say, hey, I want this base pointer to go back and point at what it was pointing before. If we want to do exactly that, it's easy. We're just going to pop this value to the base pointer. If somewhere in the program here, we're going to say pop to the base pointer, then when we are right here, then this value 0013 is going to go here. And if this value goes here, then the base pointer is going to go back and point right there. And that's very important. Why we need to do this? Because maybe this is an important step for another function. Okay, we're going to talk about that in more details. So that is the push and that is the set. Okay, so here we set it. We set the stack pointer to the base pointer. So we set space pointer to what? To the to ESP. All right, so we assign the value of the stack pointers to the ESP. All right, so this is done by whom? By the code or the callee. All right, this is done by the callee. We're going to look at some examples, but I want you to understand this fact. Okay. If any registers, we can store the value of any registers just by pushing them inside, or we can have local variables as well. You can do whatever, it's a frame, you can store it. But remember, these are all related to whom? To the callee. If you want those similar things to be true in here, do them before you call the callee. So you're gonna maybe have them in here. It depends on the problem you solve, right? So this is just to show you how the frame works. All right, so we're gonna look at the stack parameters, right? Let's look at the parameters. When you talk about parameters right here, we're talking about the caller, right? Or maybe the callee. Let's focus on one of them. But I hope now you understand what's the frame, what is the base pointer, and how the base pointer and the stack pointer work together in order to help referring or help in terms of referencing between callee and caller, okay? So the base pointer does not grow and shrinks in a very unknown way, but it's very known, or I'm going to say it's not unknown. It is at a very fixed rate. But the stack pointer, we don't know. It depends on how many calls we have. All right, so this is very important. So now we're going to look into stack parameters, how to store parameters into the stack before you call another function. Okay? So let's do this exercise together, guys. All right, so now we are moving the offset of the array. We are taking the address of this array, right? And we assign it to ESI. We are taking the length of this array. It has multiple elements in there. We count them. The length is going to count them and assign them to ECX. And then we are moving the type to EBX, right? And then we are calling what? We're calling the dump, right? So this is something that we already did before. All right. So why we need the stack? If we can really push parameters or the stack registers or the register values into the stack. Why we need the stack? Why we need parameters? Why we need the base pointer, and we need to refer from a callee to caller or caller to callee? The problem is limited by the number of registers. What if you have a function one that has parameters that are greater than 8? Because you only have 8 registers. You can push if it is less than 8 or equal, you're fine. You don't need to have parameters stored in the stack. You're just going to use registers right away. Why do I have to pass parameters? Just use registers. But if you need to pass a function that has multiple values, more than 8, then it's not going to work because you have limited registers. So you need to use the stack space. And in order to use the stack space, you need to understand frames. So the fact right here for this particular problem, we don't need to use the stack at all, right? Because if we want to know the values, we just refer to them using the register name, or we're going to push those registers into the stack, and we're done. But what if we need more? So if we need more parameters, 8 or more, then we have to use the stack. So that is the motivation of why we need the stack parameters, not the register parameters. Okay, so this is the idea. We pass the arguments, right? So if we want to pass arguments inside a stack, then we're going to do it in a very simple way. All right, so let's look at this together, guys. All right, so if we want to pass a value inside a register, so this is like value 1 and value 2. These are memory 1 and memory 2, right? This is the public memory, the data memory. And we're going to pass, and we know when we pass, we either pass by argument or we pass by value, or we pass by reference. You know that in Java or in a high-level languages like C++ or Java, you already know that objects are passed by reference. Can you think about why we pass by reference? Okay, I will show you the reason, but I want you to think about it. Why I have to pass the reference? When I say the reference is the memory address, I'm not passing you 5, I'm passing you the address that points at 5. Okay? If I pass you the address that points at 5, I don't care if that address points at 1 element or 20,000. You just pass me the address, and that the address is 32 bits, so you're passing me only 4 bytes. Instead of passing to me thousands of bytes, you're just going to pass the reference. So if the data structure that you need to pass as an argument is really large, you should not pass it by the value, because you're going to pass a large, right, space. So instead, you just say, hey, you pass me the reference, and knowing the reference, we will know where to go in the memory and retrieve or use the values there. Okay, so here we're going to focus on passing using a value. So if we want to pass using a value right here, all we need to do is say push and push. If you notice, we say push what? Push val2 first, and then push val1 second. It's the idea of the stack, right? If you want to access 5 first, then you have to push it the last. That's like the basic idea. But right now, you have 6 and 5 inside the stack pointer. Don't worry about these. They mean nothing in here, okay? Just have the value. These they points at the data memory. So the stack pointer now points at the top of the stack, okay? So if I want to draw this and help you right here, I want you to understand what's going on. So if that was, imagine that was the stack is pointing at something, I don't know what it is. And we say push right here. When we say push, we are pushing what? We are pushing 5. So we know push is going to first what? Decrement by 4. And then it's going to push what? It's going to push 6. Then we're going to push the second val1, which is 5. Again, it's going to decrement. So this is no longer there. Okay, and it's going to go right here. And then now it's going to push 5. So the stack pointer is pointing here. Keep that in mind. Okay, so this is exactly what it is. And then right now we have what? We have call. We know call, what call does, right? So call is nothing but what? A push. So it's going to decrement this by 4, and then it's going to have the return address here. That's what's missing right here. You see what I'm talking about? So it's going to say that is the return address. And we know what the call is going to do else. Is going to update the instruction pointer as well. So now we know that the instruction pointer and the stack pointer. We're going to also add the base pointer as well. But this is something that you should know by now. All right, guys? So let's go to the next slide right here. And this is when we are passing by reference. If you have an array and this array is really large, or you have an object, a data structure that really has a different type of data and it's like the amount is really large, then we don't need to pass them by value. We can pass them by reference. I will show you an example in a second, but this is just a basic example. Here, when you say push, you are pushing the offset, the address. So what you find right here, the address, not the value. So if you want to access the value, you have right here, let's say if this is 5 and this is 6, imagine, if you want to access 5 or 6, you're just going to pop this into the ESI. Remember, you're just going to pop this into the ESI. And then from there, you're going to access indirectly that value. I will show you an example in there, but this is the whole idea of passing by reference. Okay, so just imagine this array. It is a D word. We know this is a 4-byte word, right? D word is a 4-byte memory. By 50, right? So here is going to be what? It's going to be a 200-byte data structure, right? Which is an array or a list right here. You should not pass the entire thing. That is too expensive in terms of the stack, because the stack has a limited space. So in order to do this, what we did right here, and to avoid this, what we did right here, we pushed what? Offset array, offset of the array. So we are just passing 4 bytes. 4 bytes means the address. So we know that this array, remember that, right? This array, it points at the first value, let's say, which is 0, let's say, imagine, and it is gonna go up to what? The 200. So all I'm passing is the address, because this name is, it has a reference, right? It's 00, if you remember, 00, maybe 0004. Maybe we are only passing the address. Maybe this is the address, and we are passing this address through what? Through the push. So we are not passing the whole thing, we're just passing the address. So that is what you're gonna find in here. That is the offset. And then we're gonna have what in here? Called the array fill. So we know that the stack pointer was here, and then it's gonna go right there because it was right here. And then when we say call, is gonna be decremented here. And then the address of the next instruction, whatever comes in here, it's gonna be pushed as a return address. And then we're gonna move to whom? To the callee. And you can see that the callee does something, because that's the beginning of the callee. This is what the callee does. Remember in the beginning of the slides, we said that the calling function, it's just gonna push whatever the parameters you have and the return address. And the called function, or the callee, it's gonna push the base pointer and is gonna set the stack, the base pointer with the value of the stack pointer. This is a fundamental thing to have in mind, okay? All right, so let me move on to the next example, which is accessing the stack parameters. So let's say if you pass parameters in here, either by reference or value, and you need to access them. All right, so let's look at those. We're gonna look at this example right here. This is something that we already looked at, and this is add2 function, right? And it passes 5 and 6. All right, so if you wanna do this right here, then we know that 6 is gonna be first pushed into the stack, and then it's going to be 5, and then we're going to call what? Add2. This is how we're going to translate this. We're going to pass this by pushing it, we pass 5 by pushing it, and then we're going to go add2. This is how a C-like languages work. They're going to push arguments right to left, okay? Other languages, they might push left to right, but we're just talking about C or C-like languages. So this is exactly what happens when you say call add2, right? In a high-level language, and you're gonna say 5 and 6. This is exactly what's gonna happen. So you're gonna get 6 first, then you're gonna get 5, and then we're gonna get the return address, which is the address of the next instruction. And then now we're moving to the calling function. To the called function. Okay, so this is very important. Let's look at the example right here. So if you look at this program, we have 2 space in the memory, 8-byte space of memory. And now we are pushing, passing arguments by value, like the add2, if you remember. And we push val2, val1, and then we are calling what? Add2. So we push this, the stack pointer was somewhere right here. And then the first push is gonna bring it right here. The second push is gonna bring it right there. And then the call is gonna bring it right here. Okay, And then once we say the call is going to do this, and then the instruction pointer is going to now move from the next instruction. Instead of that, is going to go and point at the first instruction. So now that is the instruction pointer. So there is a difference, right, guys? We're talking about dot data memory. We refer to it by value. We're talking about the stack. We refer to the stack by using the ESP, the stack pointer, or the base pointer. If we're talking about the code, we need to go to the code memory. Then we are talking about what? The instruction pointer, because that is the register that controls the dot code memory. Okay, so once we go right here, the first instruction is going to be what? Push the base pointer. So push again is going to do what? Decrement by 4 and assign the base pointer. Just imagine here you have the base pointer. And the base pointer in the memory doesn't have to be a stack memory. The base pointer was pointing somewhere in the memory, okay? It was pointing at this part. So now we said, okay, save the value. Let's say it's a stack pointer, as I said before, this is 0013. Just imagine that is the value inside this register. So this value points here. So what we did here, we say, take this value, push it, and store it right here. So you're gonna have 0013. And now we are ready to update the value. So the value now, this value points right here. We wanted it to point right there, but we don't know what that value is. So we said, okay, we know who points here. Okay, so who points here is the stack pointer. Okay, but the question is why the stack pointer points here, right? Since we did the call, when we did the call right here, it points right here. And when we do this push, it's gonna push right here. So when we did this push, when we did this push right here, when we executed this push, it's gonna decrement and bring it here. So the stack pointer points right here now. So we take that value, okay, and we assign it to the base pointer. So just imagine if this value of the stack pointer is 00, let's just say 24. Okay, just imagine this is the value. So now we're gonna change this value from this into what? 0024. So if you do this, this is gonna directly go and point right here. So now we have the base pointer and the stack pointers, they're pointing at the same thing. Okay, so if you wanna push the stack, or if you wanna add value to the stack, we don't care anymore because you have a fixed point. But something common that my students really have hard time with, when we say the base pointer inside, that is nothing that we use to refer to anything in here. We just saved the old base pointer value. So that way, when we return, we're gonna get it to point at, when we destroy this frame, the frame that comes in here, when we destroy it, we want this value to go back to the base pointer. So the base pointer is gonna go and point at whatever it was pointing at before, okay? So now if you want to continue, the whole idea here, we have to access, right? I'm just repeating myself, so I know this concept's a little bit complicated. So just I hope that every time I repeat it, you're going to get a little bit better. I mean, it's going to get a little bit better. So here we have the base pointer. So we have a fixed point. That is the base pointer. That is what we have right here, okay? I'm sorry. Okay, that is the base pointer. So we're just going to imagine it's 240024, whatever that value is. We don't care. But whatever that value is, add 12 to it, right? So if you add 12, just say 4, 8, 12. Then you are right here. Okay, if you are right here, then you are reading what? You are reading 6. Okay, if you want to refer to 5 and you want to access the parameters that already declared inside the caller, this is all the caller side, right, guys? And I'm right now at where? At the callee, at the callee side. Okay, so if I am at the callee side and I want to access something in a different memory of a different function, that's how the frame is going to help you, because you already framed your stack space with the base pointer right here, and then you're going to say I want to go 8, so that's 4, 8. Then you're going to access 5. You see what I'm talking about? So this is very important. So you can access this, you can compute whatever you do, because this is at 2. And then now you're gonna say what? Pop. Okay, why we need the pop right here? Okay, we need the pop. What if we don't have the pop? What's gonna happen? Just imagine if this is not here. This pop is not here, right? We know a fact when you guys learned the stack as a data structure, every push instruction must have a pop. you already have a push in here, then you must have what? A pop. That's a basic idea. But there is another reason. I'll explain that one later. What if we do not have this? It's okay, but it's going to cause a problem. What that problem is, I will explain it in a minute, but you can think about it now. Okay, but anyway, if we say pop right now, we know what pop does, right? It does not decrement. It copy first and then increment. And the push, it does not copy. It first decrement and then push. This is important too, okay? So if we want to do this right here, so we're going to just say pop. Then pop is going to do what's going to copy this value, which is 0013. It's going to copy this to where? To the stack, to the base pointer. So if the base pointer now has 0013, then it's going to go back and it's going to point at whatever it was pointing before. So we get the base pointer pointing at whatever it was pointing to before. So we're safe now. Okay? And then after that, we know what the pop does, right? It copies and then it's going to do what? It's going to increment or decrement is going to increment the stack pointer. So the ESP is going to point here right now. Okay, so that's how the pop works. So keep that in mind, please. So now we say we hit what? Return. We know how return works, right? So return, now the stack pointer points at the return address, right? So it's going to copy this value to the instruction pointer. So the instruction pointer is going to have the return address, okay? And once after it copies, since it's a pop instruction, it is going to what? It's going to add 4. So the ESP now points right here. You see it? And then the control now returns to whatever comes after this instruction. Okay? So that goes back to my point here, and that's why you saw this phase right here. What if we don't have the pop? Okay, so just imagine if we don't have the pop. If we don't have the pop, then the stack is not safe. We need to clean it. When we say clean it, we are not going to remove data. We just want the stack pointer to point at a specific space or at the right, it's going to point at the right place. All right, that is very important. So when we mean cleaning, please keep that in mind. We are not deleting anything. We're just adjusting the stack pointers to point where it should. Okay, so let's look at the idea of the stack pointer right here, cleaning the stack pointer. All right, so I'll motivate you with an example, because if you do not clean the stack, you're going to have memory problem. That's memory leak examples in some situation, or you're going to actually crash the entire program if you don't really clean the stack. If you do not clean the stack, means keep that in mind, please. Clean means we just trying to make the stack pointer points out at where it should pointing, or it should be pointing. Okay. So if we have this example right here, let me show you, right? You will play with this example in the lab. So you will see that in more details there. You'll find more instructions in the lab slides. But right now, if we're going to say call example 1, we know how call works, right, guys? Right? So the call is just going to push the address. The ASP, remember, always points somewhere else. So it's going to decrement it by 4, and then it's going to push the address of the next instruction, which is the address of exit, is going to push it right here. And then now the control is going to move to the first instruction in the callee. And we notice in the callee, we did not use the base pointer, right? So you don't have to. But if you don't do it that way, it's really hard to use the base pointer as a reference. But you can do that, okay? You can ignore it, but it's going to be hard to access parameters, because you're going to rely on the stack pointer. And we know the stack pointer shrinks and grows at unpredictable rate. Okay, it's hard to predict rate because it's predictable, to be honest. But let's go right here. We say push. So again, push always going to do what? Decrement and then push 6. Decrement and then push what? 5. So the stack pointer points right here. And then now the next thing is going to be what? Call, right? So it's going to decrement, and then it's going to say the return address to example 1, right? To the example 1. Just going to make it this way. So we assume we're going to go to the add to, and then the add to we're going to return. So when we hit the return, so this add to is a method, and it has its own return, right? That's why we're going to return to this example 1. So in the add to, when we hit return, the return is going to copy this return to the example 1, right? The return in the add to. and then it's gonna make the instruction pointer, it's gonna assign, that's what the return is gonna do, right? It's gonna assign the return address, okay? The return address to the main. Sorry, to the example one, I'm sorry. Return address, not return M. Return address to the example one. It's gonna pass it here, so the control is gonna go back to this. That's the address of the next instruction. And then once we do this, then the pop, after updating the instruction pointer, is gonna get the stack pointer pointing here now, right? So now we are hitting what? Return. Is this the return address? No. What's gonna happen? Blind. Return is blind. It's gonna pop 5 to the instruction pointer. So it's gonna get the instruction pointer here, and it's gonna have what? 5 assigned to it. Is that a return address? No. So when it do this, or when it did that, it is gonna actually cause a problem, because that's not a return address. The CPU understands that there are specific addresses that are very unique, and there is a table that has return address table. This 5 is not among those values. So the operating system is gonna say crash the program. I will show you this example in the following week, but today I just want you to understand the theory. So when the stack pointer is pointing here and return is gonna say return, it's gonna pop 5 to the instruction pointer, and the stack pointer should go and point right here. But by the time the instruction pointer needs to go back from here to the main exit, that's not gonna happen. So the program is gonna crash. So what is it that we need to do? So what we need to do is we need to keep this, or clean. That's what I mean by the clean. We want the stack pointer to point at the return address. And we know we have 8 bytes to cross, right, from here to there. So if we add 8 to this part, then now we are ready to be here at the return address. Then we can call the return. So there must be something in here done in this space before we calling the return that should take the stack pointer, or should make the stack pointer points at the return address, not at 5 or 6. Okay? So if we want to do this, this is what we're gonna do. Okay, you're gonna see the explanation that I was talking about right now, right here. So we have 2 ways to do this, guys. We either do it using the C calling convention or the STD calling convention, either way. And we will see the difference and why you need to use what. And that's sometimes, it's not controlled by you, it's already decided by the compiler. But it's good to know which one is used in the language you are adopting or you're using. Okay, so if you look at this example again, we have this problem. So when we return right here, we clean the stack. We say add to the stack pointer what? 8. So now we're making the stack pointer pointing here. Then if we say return, return is gonna pop blindly because it believes. So it's gonna go to the instruction pointer and it's gonna have the return address to the main. So it's saved now. Without this, it's gonna crash. You will see that in the lab. Okay? So the idea here, we did when we used the C calling convention, we did that at the calling function. Okay, or at the called function. All right, we did this cleaning at the called function. And then now we're returning the control back to the caller. All right, this is one way to do it. The other way to do it is to use the STD calling convention. So right here, you do it when you are at the add to, remember? This is something that you did here in the caller, because example 1 calls add to. STD convention, you do it when you return from the callee, right? But when you use the STD call right there, you do it at the callee side. So at the callee side right here, you're gonna say return what? Return 8. So return 8 means, it says what? Return to the caller and add 8 to the stack pointer after you return. That is gonna be very important. Do you see what I'm talking about? So after you return, add, okay? But right there, if you see it here, this is before you return, do it here, okay? But this is after you return. This is very important. So that's why I provided the lab exercise, and I hope it's gonna help you understand that observation. If not, you're gonna be ready for me to teach you the details in the following week, okay? But this is what I want you to understand. You pass 8 or 4, it depends on the space that you need to clean up, okay? If the stack pointer is 8 bytes away from the address point, or the return address, I'm sorry, then add 8. If it's 12, add 12. If it's 4, add 4, okay? And then now we're going to talk about saving and restoring registers. This is straightforward. If you are right here and you're going to restore registers in here, that is straightforward, okay? And the way you access them is just even easier. So you're just going to say push, push, right? If you are right here, you're already on the Koli side and you want to save ECX and EDX, you're just going to push those values there. And if you want to access base pointer plus 8 right now, you're going to go up. And if you want to go down, you're going to say negative what? If you want to access EDX, you're going to say the base pointer minus 8 because you're moving in the opposite direction if you want to access EDX. Okay, so this is like a straightforward. Local variables, they are very important. How to access local variables is very easy, but how to store them is very interesting. Let's look at them, and then we're going to end it right there. So this is usually what we do if we are in a high-level language, right? If we are coding in a high-level language, this is how we declare a space, right? Correct, guys? Okay, so if that is the case right here, then we're going to say integer. So we know we need 4 bytes for this integer, signed integer, and we assign 10. And we're going to say integer again, 4 bytes, and then we're going to assign 20. Okay? Excuse me. Okay? So the whole idea is very simple for you because theoretically it should work, but you know why you're taking this class, right? You need to understand how a software interacts with the hardware. Theoretically, it looks good, but I want to think about it in terms of hardware. This cannot be assigned a default value at the assemble time. Can you think about why that is the case? Why you cannot assign a default value at the assemble time? Okay, it initializes it at the runtime. Why? Because how do you know that the function is being called? Unless the function is being called, you never know whether there is a space for that function in the stack. So this is really hard. How can we reserve a space for something that is not yet there? Just imagine if you are now and you're imagining you're gonna have a kid 20 years from now, and then you're gonna say, oh, I wanna do this, this, and that. And maybe, do you know female or male? Do you know, is it at what age? You never know, things are gonna change. It's the same in here. You're having a main function that calls a function if there is a reason. Maybe it's not gonna be called at all. But if it's going to be called, then we will know at the real time, or when I say the real time, when you executed it, we will know exactly, yes, it is there. If it is, then go and create the space. So we don't really know whether is it going to be called, but if it is going to be called, we need to figure out a way. So we know that there's going to be a frame, and we know that that frame call or callee, and we know the callee is going to should use the base pointer. If that is the case, then we have a theory. We can say, okay, if you create a frame for using the callee side, then just subtract 4 from that frame. So if this is a stack, and if there is a caller right here, and we know the callee will use the base pointer, if the callee creates the base pointer, subtract 8 bytes. Okay, subtract 8 bytes. Do not use those because I need them for the local variables. Where those gonna be in the stack, I don't care. Just if you decided the value of the base pointer, wherever that thing is, subtract 4 from it. So that's a very efficient way. Okay, subtract 4 bytes for X and 4 bytes for Y. So this is a very interesting way to think about how local variables actually how we reserve a space for local variables. Okay, guys? So this is exactly what the implementation of this whole thing is. Okay, if you look at it right here, so this is how we create this space. All right, so right here we say push the base pointer, that's my base pointer, and then we say subtract 8 from the stack pointer. So the stack pointer now points here, right? Because we say push. So push is going to decrement, point right here, and then it's going to push the base pointer, or the base pointer maybe was pointing somewhere right here. We say no, save the value here, and then change its value, right? We say change its value, and we makes it now point right here. But it's not our concern right now. We are not focusing on the base pointer. We're focusing on the stack pointer. So the stack pointer is pointing right here. We said, okay, subtract 8 from here. If you subtract 8, you're getting this out of the space, right? So this is the space that is reserved. Okay, this is reserved for the local variables. Anything after here, which is this space, it's up to you to use it. And that is the very interesting part. You know, right? We already learned the PTR, the operator PTR, right? So we're just going to say, okay, this is the base pointer. If you created it and you assigned it a value, subtract 4 from it. That is the base pointer, and assign 10. So the 10 is going to be assigned here. For this part, if you created a base pointer, subtract 8 from it and assign it what? If you are here, subtract 8 and assign it 20. So this is how local variables are actually being created or initialized in the stack, because we know local variables exist inside the stack, not on the .data. .data is going to be the public, right? It's the public data. So that's really very interesting. Okay. So what if you did not have this? Okay. So what if you don't really have this? Move the base pointer back to the stack pointer, right? And then you're going to pop. So this, again, you're not cleaning the stack. All right. So you have to be careful about this. Just play with it. All right. So if you are right here and you say move the base pointer to the stack pointer, right? So what happens if we don't have that? If we do not say that move the stack pointer to the base pointer, what's going to happen? Can you think about it? So if you don't have that one, then here is going to be what? Remove locals from the stack. Okay, so if you want to remove locals from the stack, you're just going to move the base pointer to the stack pointer. And that way you're going to get the stack pointer point at wherever you want. And in that way, now you're going to get the stack pointer right here, the base pointer popped out. Okay, so you're just going to pop the value out to the base pointer, the value that you stored right here. And then the base pointer now is pointing somewhere else. So if you say -8 or -4, it is not clean right here. So you have to be careful. So these two things, they're going to help you in terms of removing. Okay? And if that is the case, when we say this one pop, if we're going to say this one pop, we're going to copy this value, and then the stack pointer, we know that this is how the pop works, is going to copy the value. The stack pointer is going to point right here, and then the stack pointer now is going to point at the return address. So is that safe to return? Yes, it's safe. Okay? So I'm going to stop right here, and we're going to continue the following week talking about reference parameters and recursion, which are two very important concepts, but recursion is a key thing. So you're going to see a very interesting example in the lab. Try to play with it. Try your best to play with it. So that way you're going to be really ready to for us to move on to the next step, because recursion is nothing but the application of frames. So whatever we learned today is something that you're going to see very much applied when you use the recursion. We're going to explain that in more details in the next class. Okay. So for now, I would like to thank you guys for your time, and let's see if we can meet on the following week. Thank you. Take care.